Hello students, in this video we'll see that Hamiltonian flows preserve area. Let's consider the Hamiltonian system. X prime of t equals negative hy, we'll make that a positive, and y prime of t equals negative hx. And so what we'll do is we'll call this function hy over here f of xy, and we'll call this function y prime over here g of xy. And we'll let phi of xyt be the flow. And so the flow is a vector field. And we'll say that this flow has coordinates xc, xy, t, eta, xy, t. Now we know that since this is the flow, we know that xc, t, xy, t is going to be f of xy, which will be f of xc, xy, t, eta of xy, t. And the second coordinate, eta t of xy, t, will be g of xc, xy, t, eta xy, t. And so now we'll note that let's let omega be an initial region, and consider the evolution of omega under the flow. So we'll consider phi of omega t. We'll call this omega t, and we'll call the initial omega 0 will just be the set omega. So we now know that we would like to figure out how the area is changing. So the area, t, is the integral over omega t dx dy. And these are dummy variables, so I can change them to whatever I wish. And we know by the change of variable theorem that this will be the integral over omega of the absolute value of the determinant of the Jacobian of the transformation. And so the transformation, of course, will be the phi transformation, so it'll be the Jacobian of xc and eta with respect to the x and y coordinates, dx dy. And so we can actually write down what this is. So this Jacobian, so the determinant of dc d eta dx dy will just be the determinant of partial xc partial x, partial xc partial y, partial eta partial x, partial eta partial y. And so what we'll do now is we'll compute the derivative of this with respect to t. So what we'll do is we'll look at a of t plus h. So a of t plus h will be the determinant, this integral over omega of the absolute value of the determinant of xc x t plus h, xc y t plus h, eta x t plus h, eta y t plus h, and then I'll have a dx dy. And so now we can note that to first order, this will be equal to first order, the integral over omega of the absolute value of the determinant of, we'll have xc x as a function of t plus h xc t x, and then xc y of t plus h xc yt, and then eta x plus h eta xt, and then eta y plus h eta yt dx dy. And so now we'll use the following fact for matrices. We'll use the fact that the determinant what we have here is we're going to have a matrix, let's say xc x, xc y, and then eta x, and then eta y. We'll have our initial determinant plus this determinant over here, h xc xt, h xc yt, h eta xt, h eta yt. And we can split this into several parts. We can write this as the determinant of xcx plus h xcxt, xcy plus h xcyt, and we'll keep the etas on the bottom, eta x, eta y. Plus, we'll keep the xc's constant now, xcx, xcy, and then we'll have eta x plus h eta xt, and then eta y plus h eta yt. And now we'll use the fact that the determinant is multilinear, which in the next video we'll use the multilinearity of the determinant, and then we'll do the next approximation to see that this will give us an expression that involves the divergence of the vector field. Continuing our solution, we see that a of t plus h is the integral over omega of the absolute value, which I'll suppress, of the determinant of xcx, xcy, eta x, eta y, plus h times the determinant of xcxt, xcyt, eta x, eta y, plus h times the determinant of xcx, xcy, eta xt, eta yt, and all of this will be dx dy. And this first integral over here, this first portion, is exactly just a of t, and then we'll have a plus h integral over omega of these other two determinants. Determinant of xc, xt, xcyt, eta x, eta y, plus determinant of xc, x, xcy, eta xt, eta yt, dx dy. And so we'll focus on these other two determinants over here, recalling that xct is f of xc eta, and that eta t is g of xc eta. We can find each of these second derivative quantities. We have xc xt will be f xc, xcx, plus f eta, eta x. xcyt by the chain rule will be f xc, xcy, plus f eta, eta y. And the corresponding results for the eta x and eta y, so I'll have eta xt will be g xc, xcx, plus g eta, eta x, and eta yt will be g xc, xcy, plus G eta, eta y. So we will plug this in. Let's look at the first expression over here. So this first determinant, we'll call this determinant number 1. Determinant number 1 will be the determinant of f xc, xcx, plus f eta, eta x in the first entry, then f xc, xcy, plus f eta, eta y, and then I will have a eta x and an eta y. And if we break this into two parts, we notice that this term and this term over here will be a multiple of the second column, the second row, and so those determinants will go away. So this will go away and this will go away. And we'll be left with a factor of fxc, which we can factor out. So I'll have an fxc, and then I'll have the determinant of xcx, xcy, and then a eta x and an eta y. So that's what my first determinant is over here. And then similarly, if I do my second determinant, number 2 will be the determinant of xcx, xcy, and then I will have a gxc, xcx, plus g eta, eta x in the first column. In the second column, I'll have a g xc, xcy, and then a plus a g eta, and then eta y. That'll be my eta y terms. And when I compute the determinant of this, I notice that if I look at these terms over here, those terms over here are gxc, xcx, xcy. That is a multiple of the first row, so those terms will drop out in this case. And I'll be left with g eta, so I'll have a g eta, the determinant of xcx, xcy, eta x, eta y. And those are my terms with an h. So what we have here is we have that a of t plus h is a of t plus h, and then this expression times what we have previously. So we will have from our formula that a of t plus h is equal to a of t plus h, and then I will have the determinant, these two determinants over here. Those two determinants are exactly what we see in the a of t relationship. So I'll have the divergence of the vector field fg, and then, so this is to first order, and so what will happen, so we'll put order h squared terms over here, and so I will have a of t plus h minus a of t over h will be the divergence of fg plus order h terms. So this will tell me that a prime of t is the divergence, and I should have an a of t over here as well. A of t is the divergence of fg times a of t. So in particular for Hamiltonian systems, so divergence of fg is the divergence of hy negative hx for a Hamiltonian system, and this will be hxy minus hxy equals 0. So for Hamiltonian systems, this becomes a prime of t is equal to 0. And this a of t, of course, is because this matrix over here is our a of t matrix when I integrate it. So I'll have the extra a of t over here, this extra a of t over here, and consequently the a of t over here. So for Hamiltonian systems, a prime of t is equal to 0, and that says that a of t, the area that is moved at time t, is exactly the same as a of 0, and therefore Hamiltonian systems preserve the area of the region under the flow.